Bismillah ar-Rahman ar-Rahim. So we stopped here last time. We talked about fragmentation, and we talked about the main function of the network layer, which is routing. We talked about IP address. So today we'll continue digging into the header fields of the IP version 4 standards. So the next field we will talk about is the type of service. Remember, in the beginning of the course we talked about the very important concept of quality of service. We talked about the fact that quality of service will discriminate between the different types of data, right? So this field is used to facilitate this. So the type of service is a field which is it's 8 bits, except that only 5 of them are being used. 3 of them are not being used. So the least significant 5 bits are used to represent the type of service. And the type of service is really defined in a very high level way when it comes to IP version 4. And that's one of the disadvantages of IP version 4. So the way it's used is that the host itself, at the beginning of the transmission, sets this field to indicate that I'm sending video, I'm sending data, I'm sending whatever. Okay? So the router in the middle of the communication will read that field and will try to give some priority for that type of data based on the value of this field. So for example, if it's a video, then it knows that it has to deliver it right away. It delivers it very fast. And if it cannot, drop it. Because this is video. This is the best behavior for video. If you can deliver it now, go for it. Otherwise, drop it. Because if you deliver it like a few seconds after, I don't care. It's too late anyway, because of the streaming nature of video. If it's data, keep it in the buffer, deliver it whenever you want, but please do not drop it, because if you drop it, then the whole data will be corrupted. I mean by data is like a part of a zip file or actual executable or something like that. So if you lose any part of this data, it's all gone. So the type of service is used to do that. The problem with that is that, this type of service is only 5 bits. So 5 bits will give you maybe 2 to the power 5, like 32 types of data. So nowadays we have hundreds of types of data that we use, and each one requires different requirements when it comes to quality of service. There is online video, there is offline video, there is online data, there is offline data, there is banking data, there is different types of data. So this type of service is definitely not enough to have a good granularity in the sense of providing good quality of service. So that's one of the disadvantages of IP version 4, which has been resolved fundamentally in IP version 6, which we will talk about later. The other thing here is that this type of service and IP in general does not really distinguish the specific session end-to-end. So for example, you want to give a specific quality of service for a specific end-to-end communication. Okay, so the router itself receives data from multiple networks, from multiple hosts. But it has no idea to figure out that this is coming from this particular application on your host, on the source, right? Nothing here identifies an end-to-end session. So I cannot provide quality of service per flow. I can only define quality of service based on the type of data in this TOS field. That's all I have. I don't know whether this field belongs to this application or this application or this application. So, for example, you may have multiple video flows coming from different servers, from different types, from different ASDI locations. You may want to discriminate between the different applications. Here you cannot do that. Here you have like one value type of service is video. But you have no idea of discriminating between the different flows of video. Okay, here you don't have any actual discrimination between the different applications. So this is a rough support or a high-level support for quality of service using the type of service. This is the only field used for quality of service. In IP version 6, they use different fields multiple fields together to provide more granularity on the quality of service you provide per flow. And you can distinguish between the different flows, the different applications, different types of data, and so on. So that gives you more control. So the type of service here, as we said, discriminates between voice over IP or streaming video or different or actual data and so on. So that's regarding the type of service. Another very important functionality in IP version 4, which is what we have touched on last time, is fragmentation. So we said that when the host first sends the segments, the host has access to know the type of medium that it uses. And of course, if it's Ethernet, then the maximum segment size will be 1480. Okay? If it's wireless, maybe it's going to be less than that. So based on this, the source will send the data with the IP header or the data with the TCP header to the network layer. The network layer will then create the IP header. The problem with that is that if it happens that this data passes through another router like this one, and then this router figures out that this particular medium has a different maximum segment size. Well, if the maximum segment size is more than 1500, then I'm fine. I don't have to do anything. I can fit a fragment of 1480 or 1500 in a maximum segment size which is more than 1500. I can do that. It's like you are putting a 1500 volume of an object inside another volume which has, or another tank which has a bigger volume. So that's possible. I can do that. I don't have to do anything special. The problem comes if you have to do that, if you have to fit this big segment or big packet into a maximum segment size which is less. In that case, you have to do what we call a fragmentation. In TCP, we call it a segmentation. Here, we call it fragmentation. Again, the terminology gives you an indication which layer we're talking about. Okay, so the desegmentation happens at the application on the other side. Here we have to worry about fragmentation, and fragmentation here requires multiple fields to work together. It's not as easy as segmentation, and we'll talk about why. So fragmentation here uses 3 fields in the header. Okay, if we can just zoom in a little bit here. So we use the flag, we use fragmentation offset, and we use identification. So those 3 fields are being used as part of the fragmentation. So identification is simple because it identifies the sequence of the fragment in general. The sequence of this fragment. It's only like the sequence number in TCP. Okay. The flag here is just 1 or 0. It's 1 bit to indicate 1 or 0. This represents more fragments are coming. So as long as you have more fragments that belong to the same packet, you set this to 1. If you set it to 0, then this means that I don't have any more fragments that belong to this particular packet. Okay? So we'll see it in action. We'll see it in action how we set these flags. Don't worry. Okay? Then the fragment, I'm just explaining the concept. Then the fragment offset will give you information how you can defragment everything, how you can consolidate all these fragments into one packet. Okay? Why we need this? Because maybe, as you indicated last time, which is very intuitive, I mean, one of the fragments may get lost. Because I do not have any guarantee, okay, I don't use retransmission here. So I need to know if there is any lost fragment, I need to know. Okay, that's why I need 3 fields, and we'll see now how these 3 fields can work together in order to facilitate this. Okay? So the fragment offset field and more fragments is used to reconstruct the packet on the other side. One more piece of information is that once we fragment, okay, we do not defragment until the very last router. Okay? So if you fragment here, we do not defragment here. We do not defragment here. So we do fragmentation here, and then we do not do defragmentation until here, until the very last router. That's another important concept. Okay? Once you fragment, you do not defragment. Why? Because you can defragment and then the next medium will force you to fragment again. So you do not fragment and defragment. So it's more efficient. Once you fragment, you're forced to do that, that's fine. Do not defragment until the very end router. Because once you defragment, you go straight to the end host. You don't have to do fragmentation again. Go ahead.
But for example, you said that the fragmentation can vary between 2 ends or between 2 hosts.
Right.
Yeah,
Right.
So maybe it will need to defragment a fragment.
No, you can fragment over a fragment. You can do that. You can fragment and then fragment again.
I mean, yeah, fragment and fragment.
Right. So that you can do. No problem.
Okay.
But if you fragment over fragmentation, do not again defragment until the very end router. So you do fragmentation at any point in time as you need. But defragmentation is done once. At the very last router. Okay? Okay? Type. So that's that. This is this explains that concept. When fragmentation occurs, it does not get reconstructed until it reaches the final stage, which is in that case the host, the final host. So the host will have to defragment. The final host needs to defragment. Okay? So fragment offset field identifies the order, or the fragment offset field will tell you this fragment goes into that location in the big packet. Okay? It's like a pointer. It tells you that this particular fragment points to the location where it has to be put in the actual packet to create the original packet again. We'll see that. So going back to the header, of course, I mean, it's the same concept using the version. The version here indicates the actual version. It has to match on both sides. And if both sides agree on using IP version 4, then they both use IP version 4. You cannot use IP version 4 on one side and IP version 6 on another side. So they have to match the version. So this field is important in that regard because you have to talk the same version and the same protocol. Here it's the header. So go ahead.
IP version 6 will be demoted, or it will just understand it by default?
Usually routers that support IP version 6, they also support IP version 4. So if you have a communication with another router that understands only IP version 4, then you have to downgrade yourself to IP version 4. Yes, so you have to downgrade to version, similar to HTTP and similar to other protocols, okay? But actually, in the case of IP version 6, it's even much more complicated, and we'll talk about how this is done, because it's much more complicated in the network layer. Because the network layer deals with, hub by hub communication. It deals with different routers throughout the communication end to end. It's not like end to end communication and that's it. You do like the transportation on one side and then you do TCP on the other side, and so it's application to application. Here, it's a network to network or router to router. So you have to do that in every single hub or every single router, which is more complicated. And that's why supporting IP version 4 or IP version 6 has to be done in a group of routers altogether, not just one router can be version 4 and one router can be version 6. It doesn't work this way. The whole network has to agree on one protocol to use. Okay, so here we have header length, so IP header length, which specifies the size of the packet header. Remember, in TCP it was header and it was in TCP it was the header itself. Why? Because again the header length is variable depending on the size of the options field, right? So you have to specify a header length whenever the header has a variable size. So that's why we have a header size and packet length. So we have two pieces of length in that case. You have the header size and you have the packet length. Identification, as we have mentioned before, this field is primarily used to uniquely identify the fragments. Okay, so you have to identify the fragments, not the sequence of the actual packet, the fragment. So once you start fragmenting, you set the identification to 0, 1, 2, 3, and so on. Okay? But the actual packet itself, if there is no fragmentation, then you do not have to set a specific sequence number. Because the sequence number does not have any value in that case. Remember, the sequence number is important if you have a connection context. A connection context requires the fact that you have to have a sequence number, because this sequence number belongs to this particular flow end to end. But here there's no flow, there's no actual connection. There's no actual connection. So the identification here refers only to, it helps you to reconstruct the fragments, but it does not help you to identify a specific end-to-end flow at all. Because there is no such thing. There is no end-to-end connection. Remember, IP is connectionless. Okay? So this only helps the host at the end to be able to reconstruct the packet from the actual fragments. Okay? So identification will be set to a specific unique sequence for the fragment, and as long as you have more fragments, then you set the flag to 1, okay, and then the fragment pointer helps you to locate this particular fragment in the actual location in terms of bytes, not just sequence, in terms of bytes. So the checksum field is used for error detection, not correction. The only place where we have error correction is where?
Application. No,
Is?
TCP.
Application?
No, not TCP.
That's a tricky question. We said that.
What layer?
Yes.
Transportation layer.
No. Remember, the error, the reliability in TCP is done through what? Retransmission. Right?
Yeah.
So checksum just tells me whether this segment is correct or not.
Okay.
But if it's not correct, then I discard it and I rely on retransmission. But there is only one place in the stack where we don't rely on retransmission only, but we actually need to do some error correction before we can rely on retransmission. And that's in the data link layer. Okay. Of course, we didn't study data link layer yet, but we mentioned that at some point, that the trailer in the data link layer has not only a checksum, but it's something called CRC, cyclic redundancy code. Yes, so it calculates the number, and not only does it know that there is an error in the packet, but it knows where the error is. So if it knows where the error, just toggles the bit and fixes the frame without having to rely on retransmission. Okay. And again, the options field is very much similar to TCP, and it's very much similar in the sense that it's rarely used. For TCP, as we will see later, it's in very few cases it's used for ICMP, which we will talk about. But the options in the IP header field are almost never used. This has been put as a placeholder if there is some protocol in the network layer that can work hand in hand with IP, but it turns out that it's rarely used. So this is one placeholders where they put it in the standards just for future extension, and if they need to complicate the protocol design based on some future changes or some changes that happen in the applications. But for IP, it's never used. For TCP, they found a use for it, which is ICMP, but for IP, it's never used. So that's conceptually the function of IP and the network layer. So I think one thing we've missed here, I remember there was a slide about this, but we can talk about it conceptually. So, so assume that I have a packet which is overall it's 1480, and then there is an IP header like this. So I need to break this down in case the maximum segment size is, let's say the maximum segment size is 500. So I need to break this down into three fragments. One is 500, okay, and another one is 500, and another one which is 480. So now we need to know the identification, and we need to know the flag, and we need to know the fragment pointer for each one of these. Okay? So the identification for this one, so we'll put like 3 fields for each. So this is the identification, this is the flag, and this is the fragment pointer. Okay? So basically, the first one will have an identification of 0, and this one will be 1, and this one will be 2. That's easy. The flag will be 110, bro. And the fragment pointer here will be 0, here will be 500, here will be 1000. Okay? So that's how you set these 3 fields. So these 3 fields will tell you exactly how you can reconstruct the fragments into one actual packet at the end.
So the pointer is like where it started cutting the tracer?
Yes, because the segments might not have equal size. The segments might not have equal size, or I shouldn't call it the segment, the fragments might not have the same size. So you can end up, remember, especially that this can be fragmented even more. صح?
Yes.
So you may pass into a router that has a maximum segment size of like 300. So this will be divided into 2. This may be divided into 3, and so on. Okay? So when you divide more, the identification number will be in sequence, so that it helps you to reconstruct all of them. But you still need the fragment pointer, because these segments may not, or these fragments may not have the equal size. So you need to know exactly where to put it. Okay? So this fragment size is always, and one of them may be lost. Okay?
But you need to review the whole segmentation once fragmentation is done.
Right. So yeah, so you need to know at the very end host, you need to know where to put each fragment in which location exactly, so that you can have a global idea about the whole packet, whether there is something lost, whether this is in this part or that part, and so on. Okay? Okay, so now we'll take a look at the IP addresses in details. So I think in the lab you have talked a little bit about that, and the lab instructors have informed me that they discussed this in detail. So we had some agreement that we'll still cover it. We'll try to cover it a little bit fast, but we'll still cover it, because this is basically the most important part of the course. You not only need to understand the concepts to deal with IP address, but you need to really practice and know how to do subnetting and how to calculate these IP addresses very efficiently and very fast. So it needs a lot of practice. That's why we need to give more exercises and more practices as part of the lecture and in the assignment. In assignment, I think assignment 3, you will have to practice a lot subnetting in different exercises. So the idea here is that this is what we call a subnetwork. A subnetwork is connected with a router. Okay, so what happens is that the whole network inside an organization may be divided into smaller networks, and for each network we assign a range of IP addresses. Okay, so the way to do that is either assign the same range of IP address on all locations, which I think is not efficient, and that's why they use a VLSM. Okay, so this part talks about these concepts, whether it's a fixed range for all networks, or why this is not efficient. So we need some kind of a variable range for each network, and how do we do that using the IP address and the subnet mask. So we need to define what IP address is, what subnet mask is, and how they are used, and so on. So the /16 here refers to that subnet mask. So when we say /16, this means that we divide this IP address into two parts. The first, the highest 16-bit, refer to the address of the network, and the lowest 16-bit refer to for the host. Okay, so this will help the router to detect that I need to reach this intersection or to this subnetwork. So I only need to look up in the routing table using the network address, not the host address. Once I reach to this network, I know that I'm done. It's only a matter of going to this host or that host. This is a data link layer issue, which we will talk about. But once I reach the network where the host is, then I'm done. The routing layer function is done. So that's why we need to use this suffix to indicate where is the network part, because that's what I actually use to do routing. That's what I care about when I look up the table inside the router. So host IP addresses are members of a group of addresses that are assigned by a specific organization called IANA, or Internet Assigned Numbers Authority. So IANA is an organization which is responsible for assigning specific IP address ranges to a specific organization or locations. Okay, so it's not done sporadically. It has to be done officially. So what happens is that, if you remember, we discussed in the first part of the course, we discussed the hierarchy of the internet, and we said that there is a tier 1 service provider, there's tier 2 service. You have to have this hierarchy in the internet in order to provide scalability. So what happens is that IANA deals with tier 1 service provider. They tell them, okay, so we can give you this range of IP address. Then the tier 1 service providers will say, okay, so we'll take this range, we'll divide it into more sub-ranges, and we assign to tier 2. So tier 2 will say, okay, so let's take this range and assign it until we reach tier 3, like the university here, which will say, okay, I will take my range and then I will assign it to specific sub-networks inside the university and so on. So that's how we do it. That's how we assign the IP address ranges. So we talked about IP address, we talked about the subnet mask initially, and again we'll talk about it in more details later, which is this suffix here, which helps me to divide the address into two parts. If we say 16-bit, we know that the IP address is actually 4 bytes. Each byte is 8 bits. So each number here refers to 1 byte, which means that it can range from 0 to 255, right? So 172 is the highest byte, 16 is the third highest, and then, or the second highest, and 10 is the third highest, and so on. So 16 means that the first 2 bytes, which means that 172.16. Anything else, I don't care, because this 10 and 100 refers to the host on the network. And for routing, I don't care about the host part. I only care about the network part. So what happens is that the router, actually what it does is that, we'll talk about that later, but we can mention it now quickly. Using the 16-bit, it generates 16 ones and then 16 zeros, and then it performs like AND operation between this and the host address or the actual address. And that will give you what? Will give you the network address, because anything else will be 0. Anything ended with 0 is 0, right? And anything ended with 1 is the actual thing. So using a very simple AND operation, you get you can divide the network part from the host part. You take the network part and then you use it for routing. That's what actually the router does. Okay, so whenever it receives an address like this, it performs an AND operation. It extracts the network address and then it uses it for routing. So in the Windows configuration, you have the IP address, which either gets assigned in a fixed way, or, as we said before, using DHCP, we can get assigned a dynamic address. When DHCP is invoked, the DHCP assigns to you IP address, subnet mask, and another thing which is what we call default gateway. Okay, so the default gateway here usually refers to the actual router that can be used to access the external network. Okay? So usually default gateway is one valid IP address, and usually it takes the network part could be anything, and the host part usually is a 1.1 usually, but you can assign any host part to the default gateway, and that address refers to the default address, which means that if you want to get out of this network to go possibly to the internet, this is the default route that you have to take. Okay? So if you receive a specific IP address and then you go to the routing table and you figure out that you need to go to the internet, okay? So which way to take? You go to the default gateway. And the default gateway is the only route to the internet, to get out of this network.
This is the address
to the default gateway, to the default gateway. So any host should have a default gateway, which is the default route to the external internet. The default route to the external internet, which takes you to your service provider and then go to the internet. So this refers to a router which is used to forward packet outside the network. This is your way out of the network. Otherwise, for example, if this host wants to communicate with this host, then I don't have to get out.
Yes,
I don't have to invoke the default route in that case. So it goes to the router, and the router figures out I'm still in the same network. This host exists on the same network. So it doesn't do anything. It doesn't get it outside. It actually sends it down in the stack to the data link layer, and the data link layer will send it to the physical address of that host. Okay? But if it figures out that, okay, I need to get out, so it goes to the default gateway to send it out. So that's what happens. So any host needs to have these three things: a specific IP address, which is supposed to be unique worldwide, okay? And I'm saying suppose because we'll see some exceptions to that. Subnet mask, okay, which has a significance or has valid information inside a network to help you to divide where is the network part from the host part, and the default gateway, which is your only way out to the internet, okay? So each host has to have these three pieces of information: the host, or sorry, the address, and the subnet mask, which helps it to divide the IP network and host, and then the gateway, which refers to the way out. Okay, so all hosts in the same network will typically have the same default gateway, which makes sense because each subnetwork will have only one way out. Okay. So you can perform IPconfig. I'm sure you have done this a lot, several times, whether in the lab or maybe outside, maybe before the course. You have some familiarity with IPconfig, and you can get some idea about the allocated IP, if it's dynamic or fixed, and subnet mask. So this /16 gets translated into 255.255.0.0. So you can simply AND this with the IP address to divide. It's very easy. And then the default gateway usually I'm saying usually, it's the exact same network address, .1.1. Okay. So, as I said, the service provider, whether it's tier 1, tier 2, tier 3, will get this IP range and then will divide it into multiple ranges. And the way it divides that is by saying, I have /16, okay? So I can divide that into, let's say, like 255 different networks. If I divide it into 255 different networks, I need how many bits? 8. Okay? So it allocates the third highest byte for the subnet address. So in that case, so you have the first byte and the second byte. These are network address. Okay, and then the third part, which is another. This is 8-bit. This is 8-bit, and this is 8-bit. So this 8 bytes will allow you to subdivide your network into 255 subnetworks. Okay? So here you can have, or 256 يعني, but usually the first 0 is not used, and we'll talk about why. Okay? Then if we divide it into 255 networks, then we have left only 8 bits, right?
Yeah.
Which leaves how many hosts per network we could have? 255 hosts.
Yeah.
So that's how we do subnetting. So you can have a tier 2, for example, can get a /16 range. So it divides it into /24. /24 meaning that it has 255 different networks, and each network can have up to 255 hosts. Okay, so that's how it's done. So we'll stop here.